welcome back. Our next speaker is Brandon Barker. Brandon is a Scala developer at Caesars Digital, where he's been since last year. Previously, he worked at the Cornell Center for Advanced Computing, writing Scala, Haskell, and PureScript. He has published work in metabolic modeling and genetic interactions, a rich field of examples of optimization algorithms. And today, Brandon is going to talk to us about distributed global optimization in Unison. All right, take it away, Brandon.
All right, thanks, Runar. So I'm a bit of a beginner with Unison, so this is kind of my foray into Unison. When it first came out a couple of years ago with the initial alpha releases, I tried it out briefly, and it was fun back then, and it's even more fun now. So starting out, if you want to follow along with this later and play around with it, you can basically follow this transcript, which has all the evaluated code displayed in it. So everything should just work exactly like you see it here. And it also shows you how to pull in this code base that we're going to be working with today. So as Runar mentioned, I have a bit of a background related to using optimization algorithms to solve certain biological problems. So in my case, I was often limited to using these on a single system, maybe multiple processes, but even that could be a little bit tedious to set up and to really get working well. Especially it was in MATLAB, which is it's great at a lot of things, but I think we'll see that Unison handles distributed computing quite a bit better. So when I saw that Unison was really focusing on distributed computing, I thought I should try writing a distributed optimization algorithm in Unison. And I wanted to pick something that was simple, flexible, and of course distributed friendly, and something that I'd used before. So we'll see what that is in just a minute. And also, this has just been a lot of fun to do since it's in Unison. And using the Unison Codebase Manager has been really pleasant. So big shout out to the developers for that. So the particular kind of algorithm we're going to look at today are genetic algorithms. We'll look at where they fit into the optimization algorithm spectrum a little bit, what they do, an example problem, which is going to be the knapsack problem. We'll see a little bit of the implementation in Unison and how we make it distributed friendly, and then we'll show an example run of the algorithm. So a lot of people are probably familiar with optimization already. If you're not, they are used in a lot of places you might not think of. But some of these places are AI and machine learning. More recently, that's been a very big field, of course, and traditionally they're used in scheduling, routing, cost savings, and other areas. And I've used them just for simple parameter tuning in the past, when I didn't really know what the right parameters should be, but I was able to use genetic algorithms to find a good solution there. So let's talk a little bit about how genetic algorithms operate. First of all, there are many types of optimization algorithms, and going into them is going to be beyond the scope of this brief talk. But genetic algorithms are a type of evolutionary algorithm, and you're basically mutating base pairs. So these base pairs are going to be just like a list of data, typically numbers, and you can think of that biologically as being like a chromosome or DNA. And as we've discussed, genetic algorithms are commonly used for optimization, unlike some other evolutionary algorithms, which may be doing things like mutating a program and letting it evolve over time. All right, so a genetic algorithm attempts to find a global optimum of some kind, maybe a maximum or minimum, but the thing is, it doesn't guarantee it. So keep that in mind. I'm not claiming that this algorithm will guarantee you find a global optimum. You might get stuck at a local minimum of some kind, for instance. So some of the issues with, or one of the big issues with genetic algorithms are that it requires many function evaluations. And these function evaluations may be expensive as well. It just depends on what the problem is. And the problem we're looking at today, it's not going to be expensive at all. But if you were to be in this situation, then being able to scale out to the cloud is going to be something that would really be desirable if you can, of course, afford to scale out to the cloud, right? So as it turns out, the way genetic algorithms work is totally compatible with making it into a distributed algorithm, right? Okay, so we've talked about what genetic algorithms are, and now let's talk about an example problem that we can use. Let's say you're going on a trip and you can only fit, and you're only taking a backpack or a knapsack with you. You can, you want to maximize the value of the items you're taking with you, so you rank them or evaluate them in some way and assign a value to them. Maybe you're selling the item, so you give it a dollar value, right? But the bag can only hold so much, so it could be a weight limit or a volume limit or something like that. Whatever, it doesn't really matter. But which items do you take? You can't take them all, presumably. Otherwise, you could just stuff them all into the bag. So that's going to be the problem we're looking at today. And there are many approaches to solving this. Some are specialized approaches that are developed specifically for the knapsack problem that guarantee global optimum. So if you really cared about it, and there are variants of the knapsack problem that people actually do care about, you might want to use one of those, but we can still use it to test out our genetic algorithm today. So in Unison, let's take a look. So in this code base that I have, this namespace has a few different parts. So EX is for example. This is where we've defined the item type. And this is a unique type because we don't want to get confused with other types that are also just a tuple of two floating point numbers, right? There are lots of those, probably, sorry for the pun, floating around. So a unique type makes sense here. Next, we need to basically create a map so that we can index into our chromosomes for what each item is mapping to. So to create that data structure, we're going to wrap that in a unique type and just make it a map from an item to a natural number, and a reverse map so we can go the other way from the index, which is a natural number, back to the item. And finally, we also need to add the weight limit to our problem. So we have this structural type knapsack problem that has the items in reverse and a capacity, which is a floating point number. And maybe we could have made this a unique type, but I feel like the specificity was decent, and maybe this could allow for some flexibility down the road. Anyway, let's also create a smart constructor of sorts. So make knapsack problem just takes in the possible items, the weight limit, and gives us the knapsack problem so that we don't have to also specify the reverse items up front. So we just call a helper function here for that. And there we go. We have our knapsack problem description. And we can look at where we're creating actually these problems in the code base by using the dependence command in the Unison code base manager. And what we can see is we're using it in one place called test problem 10 items. And that's the problem we're going to be looking at today. So if we look at test problem 10 items, we see that we're calling make knapsack problem with possible items that starts with an empty map. And then we just sequence together in this pure functional style, adding additional items until we have 10 items in there. And then we give the capacity limit of 200. And if you look at so remember the weight is the first part of this item. You can see that we can't fit all of those items into a weight limit of 200. So otherwise, again, it wouldn't be much of an optimization problem. Great. So now we want to look at actually implementing a generic version of the genetic algorithm, because we don't want to make this only work for the knapsack problem. So the first thing we need to do is create a base pair. So this is like our fundamental data type in the genetic algorithm. It's what the DNA is made of that we're mutating. In this case, we're creating a structural sum type that could be either a floating point or a Boolean value. And in the knapsack problem, we're only going to use the Boolean variant, but you can imagine that you might want to have other problems that take more generic information. So this could probably be expanded later to include other things, or maybe when Unison has type classes, we could think about using a type class based approach, but that would kind of sacrifice the simplicity at somewhat, I think, while increasing the flexibility. So there might be a bit of a trade-off there. But yeah, so in the knapsack problem, a 0 in the binary type would denote the absence of an item, of a particular item, according to our item map, and the 1 would denote the presence of that item. So the next thing we want to get into is modeling fitness. And we have this entity fitness type here, which is a unique type that could be, that is composed of a chromosome, which is just a list of base pairs, and a fitness value. So the idea behind this is that when we compute a fitness value, ideally we want to not have to recompute it. So whenever possible, we tag our fitness with the chromosome so we can get that back. And we have a handy little function that basically takes in our fitness function here from a chromosome to a floating point number and gives us a function back that takes a chromosome and gives us an entity fitness. So we'll be using that a little bit later. Yeah, so Stu talked about memoization, which is something I think I need to add to this later, and we'll see that. But yeah, anyway, this is a way to at least prevent local reuse of the local recomputation of the fitness values. Right, so we've talked about genetic algorithms, and we've talked about the knapsack problem. Now let's talk about how we kind of map between those two different domains. And the first thing we want to do is actually create a fitness function for our knapsack problem. So this generic fitness function takes in a knapsack problem, because there could be different knapsack problems. And then it takes in a chromosome, which is a list of base pairs again, and it will return us our fitness as a floating point value. And for this particular problem, it's relatively straightforward what that fitness should be, right? But let's look at how we get the items first. So we have to retrieve those items from the chromosome, and we have this helper function called chromosome2items to do that. So basically, we're going to convert a chromosome into a list of items, and then from that list of items, we can map over them and extract the weight here and extract the value here, and then we just sum that up. So this is just, again, using the standard functional programming approach of mapping over lists. And once we have that, we can say, all right, the item's weight is, if the item's weight is greater than the capacity, then the fitness should be 0. Otherwise, it's just the value of the items. It's pretty clear that, you know, if your list of items isn't going to fit into the bag, then that's not a viable solution. So that's why the fitness would be 0, right? I'm not going to go over the chromosome to items function in detail. You can look at it later, but again, that's just how we get our list of items from a chromosome, because we don't really have time to go over all the functions. But if we look at it, we can see it's used in a few different places. Again, we're using the dependence command, and we have the knapsack fitness function, which we just saw it being used in. It's also used in our pretty printer later. When we get back our population, we want to print out the items. And finally, it's just used in this sort of a specialized version of the function testchrome2item, which is specialized to a particular knapsack problem. So those are the places we're using it in this code base. All right, now we're starting to get into the really fun stuff, in my opinion, which is changing the DNA, which allows us to explore the solution space. The first way we do this is mutation. So during each generation, the organism, or chromosome in this case, will mutate one or more, or rather 0 or more of its base pairs. To keep it simple, we're always just going to perform one mutation. We don't really have a reason to need to do more or less than that, although we will see later that we can tune the rate of mutation. But before we get to that, let's just look at what mutation of a chromosome looks like. So we have an input chromosome, we get its length, then we use the random ability here. You can see this random ability requirement is attached to this function when it's called or evaluated. So we need that because we want to get a random index somewhere in the chromosome, right? So we use this random.nattend function to get something between 0 and the length of the chromosome. And then we use lists modify at to modify at that random index. And we call a function called mutate base pair on the chromosome. And we get back an optional value in case that was out of bounds. It shouldn't be, obviously, but if it is, we just return the input chromosome. Otherwise, we return the modified chromosome. Okay, and so we just talked about mutate base pair. What is that? Well, as we saw, our base pair is composed of different data types. So each of those data types needs a way to be mutated for a numeric value. Here, we're just going to say return a new float. For a binary value, the only sensible thing to do is to flip the bit. So that's what we do. If this wasn't exactly what you wanted, you could write a different mutate base pair function to do your mutation in a slightly different way. Okay, so the other part of changing the DNA that we can talk about is crossover, and or more generically, recombination. But yeah, crossover, I think, is what most people are familiar with, and it's what we're going to be using today. So here's a depiction of what it looks like in biology. And this image was actually created before DNA had been discovered by Thomas Hunt Morgan. He was looking at something called genetic linkage, where if you have two genes next to each other, they're less likely to be inherited because there are only a certain number of crossing over points that occur. Actually, not that many compared to the length of the chromosome, right? So it's very unlikely that that crossing over event is going to happen right in between two particular genes that are next to each other. Yeah, so this kind of illustrates the process where you have two chromosomes that come together and cross over, and then you have two new different chromosomes. So fun fact is that my first job was in a building named the T.H. Morgan building, because he was born in the same city as I was. So yeah, that was fun. But anyway, yeah, so that kind of chromosomal crossover has a few limitations. We don't really care too much probably about having genetic linkage, at least in this problem. So we're just going to make a uniform crossover function that can basically, well, if we look at it, we're taking in two chromosomes, just like in the above. We use list.zip to combine those together, and then we map over this new list. So we have a tuple of base pairs, basically. And if we get a random Boolean value and it's true, then we take the first base pair. Otherwise, we take the second base pair. And so, yeah, we basically cross over at every single base pair in the chromosome, right? Okay, so we've got our crossover and mutation taken care of. Now, let's combine those together for convenience, and also so we can tune the rates. So we have two rates, crossover rate and mutation rate. And we use the with rate function to basically, take that input function, either crossover or mutation, and create a new function that has basically the same signature, but it's randomized. So if it falls below the rate, then or within the rate, basically, then we will execute the mutation or crossover. Otherwise, we just return the original chromosome, right? So this just lets us tune that a little bit, because maybe we don't always want to cross over or mutate, right? Okay, so now the last kind of component before we tie it all together is selection. So natural selection acts as a filter in our optimization search. And we have an obligatory picture here of Charles Darwin, since we're talking about natural selection. If the fitness is too low, there's going to be an increased risk that the organism will not pass on genetic material to future generations. And we want to use that to kind of weed out our solutions that aren't doing as well. So let's look at how this works briefly. So we have a selection function here, selection random weight. We can keep the n best, but you can't really do that in nature, really, unfortunately. It would be nice if you could keep around, some of the most valuable people in society so they could keep working for hundreds of years maybe, but we can do that here. So we also have the total kept, which is the total population size you want to keep. We have an inverse perturbation factor, which is just going to allow us to kind of tune the noise that's being added to the fitness, because we don't want to get stuck in a local optima. So it can be helpful to kind of add some noise to the fitnesses occasionally. So sometimes something that's slightly less optimal may still go to the next generation. And then we have our input population, right? So in the interest of time, I'm not going to go through everything selection is doing here, but basically we compute which the current population are entity fitnesses, so we already have the fitnesses computed, and we're just going to basically be selecting according to those criteria we just discussed. And the function signature is a little bit much for passing around everywhere. We'd like something a little more generic, so we have a selection random, or a little less generic rather. We have something called selection random weight default, and this basically does the simple job of just taking in a population and returning a new population. And again, it's done randomly because we're doing we're doing the mutation and so on. Or rather, sorry, not the mutation. We're doing the perturbation of the fitnesses under the hood. Okay, great. So we have all the components. Now it's time to start to tie it together. So we want to iterate over a single generation, and we'll look at what happens there. So we have this function iterate gen default, and I wanted to show the difference between what it looked like before I added the ability to use distributed computing and after. So I got this by using the history command in Unison. If we look at diff.namespace between these two versions, you can see that some of the hashes are showing. It's because after this, the data types were further changed probably. But if you look closely, you'll see that between the two versions, they should be the same. And the only thing that's different is that we've added this remote capability to the evaluation in addition to random. So that's really the only thing that's changed in the function signature. Now, if we look at the implementation, again, I'm going to skip over some of the code here, but we're getting random chromosome pairs, right? And we use random chrome twice to get two different random chromosomes, and that allows us to do our crossover and mutation on that list of chromosome pairs. Then you have a new population of chromosomes, and we want to evaluate their fitness, right? So this is the part where we have to say, okay, we want to do this in a distributed fashion, ideally. So after we have our fitness evaluator set up, we want to get our new entity fitnesses, our new population, and we use seek.map. As we saw in Stu's talk, seek is like a distributed list. And so the first thing we do is we convert our list of chromosomes to a distributed sequence, and using from list with the parallel mode. And we could also use the sequential mode. Parallel mode allows the fitness function itself to take advantage of parallel or distributed computing if we wanted it to. So that's something that you might want to make a parameter if there was really a reason not to do that. but we're not using that here, so it didn't really matter what I picked for today. But yeah, so we get our past and present population by combining the last generation with the new generation. And we look at the size of it, and then we sort it and take the population size that we want back from the new generation. So again, we're getting the best of both worlds there, right? Right. So we want to wrap all this up into another convenience function called run generation, and that's just all that's doing. This is if you don't look at the type signature and you just look at the definition, it's just feeding in those first two parameters the mutation and crossover rates to make it easier to work with in our. So this is we're getting into the knapsack specific part of it now. This is no longer the generic code. We're tailoring it to our knapsack problem. All right. And again, if we look at the dependence function, dependence command, and call that on knapsack fitness function, we can see that the only place it's being used is in iterate gen knapsack. So this should our fitness evaluation should be totally distributed. After Stu's talk, I kind of want to go back and add and think about adding the memoization to it as well. I think that would be a good thing to have. So I'm definitely going to look into that. Right. Okay, and then finally we have a function. I'm not going to go into the details here, but it's just iterate gen knapsack is a knapsack specific function that's going to be wrapping our call to the iterate generation function that we just talked about. So yeah, great. And finally, I think this is really the last thing we need before running it. We need to be able to run a certain number of generations. So there's a number of ways you could do this, but I'm just using a simple recursive function here to run in generations. You could have like a run generations until a certain fitness value was reached. Yeah, so to do this, we can just basically recurse on the function until n iterations are reached. And so that happens when n iter equals 0, and we return the new population. And in the process, we're calling iterate gen. And yeah, iterate gen was our iterate generation function. Sorry, I should not shorten that when I'm reading it out loud, probably. Right, so that's pretty much the gist of it. Of course, you might want to go back and look into it in more detail if you have time and you're curious. But let's look at actually running it now. So before we added the ability to do the remote computations, the distributed computations, it was basically just like this. You would call a random ability handler, and in this case, we're using the split mix ability handler, which it's just a particular kind of pseudo-random number generator with a seed value that I've creatively picked as 1. And we're running our delayed computation here, and it needs to be delayed because otherwise it would try to run it immediately without the ability handler. And I guess obviously that would be problematic. Right, so we're feeding in our run generation function that we saw, which wraps our iterate generation function, and we're running that on our test problem for 100 generations with an initial population size of 30. Then, as we saw in Stu's talk, we can use remote.pure.run, and soon we'll probably be able to use the remote cloud.run function instead. So this just runs it sequentially. But yeah, it in principle could be run in a parallel fashion. Once we get the result back, we want to use the pretty printer so that we're not just looking at chromosomes. So this pretty printer takes the top number of solutions we want to look at, and we have to tell it what problem we're looking at and the population that we got back to look at. And the results are going to be a list of tuples that include the weight, the value, and I should say the sum of weights, the sum of values, which is our fitness basically, and then the list of items that correspond to that. So if we look at the result of this run, then it kind of looks, well, it looks like this. And as you can see, the top solution has a value that's very close to 200, or rather a weight that's very close to 200. And both the weights and the values tend to go down as you get worse and worse solutions. But I guess as you can see, we jump from 139 here to 166 here for weight. So it's not always the case that the weight decreases because we're sorting by the fitness values, but the fitness always goes down as you go down, right? Because there's not like a linear relationship between the weight and the value. So those could be that could cause some discrepancies between the weight decreasing monotonically. All right, so that's pretty much it. Just a fun aside is that there was no I/O used while developing this code. I/O behind some of the existing ability handlers, perhaps like remote and, well, actually not in this case because we were using remote.pure, but the random ability handler. But I think that's actually pure as well. So yeah, it's kind of amazing how much you can get done just using the Unison codebase manager. Yeah, and I'd like to thank the Unison community for answering my questions while I was working on this. It's a lot of fun, and I hope to maybe write some more optimization algorithms someday. And certainly, if anyone else wants to contribute, definitely let me know. Yeah. So that's it. Happy to take questions now.
All right, awesome. Thank you, Brandon. That was a great talk. I like how you put the whole transcript in, like this is like Unison code, like actual live code in here. It's awesome.